You know that feeling, right, when you're pushed back in your seat as a car just takes off? Or that kind of weightless moment at the very top of a roller coaster? Well, that's not just motion, it's the change in motion. We are talking about acceleration, and it's this invisible force that governs pretty much everything, from a ball rolling down a hill to a planet orbiting the sun. So let's decode it together.
Okay, so at first glance, what does a race car blasting off the line, a car just making a simple turn at an intersection, and a ball rolling down a hill, what do they all have in common? I mean, they're all moving, sure, but there is a much deeper connection here. There's one single concept from physics that unites all of them, and it's probably not what you're thinking.
You know, to really get what a change in motion is, let's first think about when motion doesn't change. We call that uniform motion. Just imagine you're cruising on a perfectly smooth highway, going in a dead straight line. If you closed your eyes, you might even forget you're moving at all. But let's be real, most of life isn't like that. It's all non-uniform motion. It's the starts, the stops, the turns. That's where you can actually feel the physics happening.
And that brings us right to the heart of it. We know acceleration is all about changing velocity, but what does that really mean when the rubber meets the road? Well, it boils down to just two fundamental ways that this can happen.
So here it is, the core idea, the one-sentence summary you need. Acceleration is just the rate at which an object's velocity changes. Now, the key word to lock onto there is velocity, because in physics, velocity isn't just about how fast you're going, it's how fast you're going and in what direction. If you change either one of those things, you are accelerating.
So let's break that down. There are only two ways to accelerate. The first one, it's the one we all get intuitively. Change your speed. Step on the gas, hit the brakes. Boom, you're accelerating. But the second one, this is the game changer, the one that trips a lot of people up. Just change your direction. That's right. If you're on a merry-go-round, even if your speed is perfectly constant, you are constantly accelerating because your direction is constantly changing. Okay, I get it. Acceleration can feel a little abstract. So how can we actually see it? Well, one of the best tools physicists use is something called a motion diagram. Let's take a look at how that works. Imagine we're like a camera, taking a snapshot of a runner every single second. If they're speeding up, the gap between each of those snapshots is going to get bigger and bigger. We can show their velocity with these little arrows, and you can see the arrows stretching out, getting longer and longer with each step. It's like a visual story of them gaining speed. And you guessed it, the opposite is true for slowing down. As our jogger starts to get tired and comes to a stop, the snapshots get closer and closer together. The velocity arrows shrink with each step, just kind of fading away to nothing. It's a really simple but kind of elegant way to see a change in motion unfold over time.
Now, this all comes down to a simple but really powerful rule. To figure out if you're speeding up or slowing down, you just need to compare two things. The direction you're moving, that's your velocity, and the direction of the force that's causing the acceleration. If they're working together, pointing the same way, you speed up. But if they're fighting each other, pointing in opposite directions, you slow down. That's really it.
Motion diagrams are great, for sure, but for a more detailed story, we turn to graphs. Specifically, something called the velocity time graph, which is an incredibly powerful tool for really understanding acceleration.
Okay, this is it. This is the single most important rule for these graphs. If you forget everything else, just remember this: the slope of the line is the acceleration. The steepness of that line and which way it's pointing tells you everything you need to know about how the object's velocity is changing.
So if the slope of the line is the acceleration, what does a perfectly flat, horizontal line, a line with zero slope, mean? You got it, zero acceleration. This is that smooth, constant velocity we were talking about earlier. No drama, just steady motion, and we can capture it in a simple horizontal line.
Now let's add a slope. A line that slants upward, well, that has a positive slope. And this means we have positive acceleration. The velocity is increasing over time. Our object is speeding up. Simple as that.
And what if the line slants downward? Well, that's a negative slope, which means negative acceleration. The velocity is decreasing. This object is slowing down. You can literally see the entire story of its motion just by looking at the shape of that line.
Okay, so we've seen the concepts, we've looked at the graphs, now let's put it all to the test with a real-world problem and actually crunch some numbers.
All right, imagine you're doing sprints. You run toward a wall, and we'll call that the positive direction, at 4 meters per second. You quickly turn around, and 10 seconds after you first started, you're running away from the wall, also at 4 meters per second. But notice, your speed is the same, but your velocity is now negative because you've changed direction. So the question is, did you accelerate?
Yes, you absolutely did. Your average acceleration works out to negative 0.80 meters per second squared. And why is it negative? Because the change in your velocity was in the negative direction, away from the wall. This is the perfect example of how you can be accelerating like crazy, even if your speed at the beginning and the end is exactly the same.
So let's just quickly wrap up what we've covered. The big idea, the main takeaway, is that acceleration is any change in velocity, and that means a change in speed or direction. We measure it in meters per second squared. Remember, you speed up when velocity and acceleration work together, and you slow down when they're fighting each other. And if you're ever looking at a velocity time graph, just look at the slope. That's your answer. So, I'll leave you with a final puzzle to chew on. A car is driving in a perfect circle, and the speedometer is locked. It's not moving from a steady 60 miles per hour. So is that car accelerating? The answer lies back in those two ways that velocity can change. Think about it. Thanks for tuning in.